Alright, so here we are, lecture 2. We're going to start by defining matter. The textbook defines matter as anything that has mass and takes up space. And I personally kind of disagree with that statement. It's a little bit antiquated and inaccurate. My definition really is that anything that composes the following subatomic particles, quarks, electrons, muons, neutrinos, photons, and energy, that is what we definitely consider as matter. Um, and this is a little bit more specific as to what is present in it. Now, for the purposes of our class, technically, quarks is what makes up protons and neutrons, which you'll find out in future lectures that ultimately is what the elements are made out of. Um, Now, the matter that we are usually acquainted with is present in three specific states. The first one is called the solid state, and simply put, this is a physical state where atoms, molecules are very close to each other, sometimes in a very orderly fashion, but the contacts are very close to each other. The shape of the solid is usually well defined. You can tell what the shape of a solid is going to be. You can tell what the volume of a solid is going to be. And usually, if you apply pressure to a solid, you won't be able to compress it. It cannot retain that volume. And the reason why is because you have all the molecules and atoms already very close to each other to begin with. Then there are liquids. Now, liquids, to some degree, have some of the structural features that the solid possesses, but a good chunk of those features have also been lost. And although you can have a volume for a liquid, you no longer have a defined shape. The liquids take up the shape of the container they may be in, or whatever receptacle they might be actually placed in. But much like solids, they also do resist compressibility to some extent. If you apply pressure to liquids, you won't be able to change their volume all that much. In fact, if you apply just enough pressure to them, most likely than not, you will get the the liquid to turn into a solid. And at that point, you're no longer dealing with a liquid. Then you also have gases. In this particular states of matter, as you can see here, you have lost all of the structural features that we had before with the solid, and that to some extent we had within the liquid. And so not only do you have no real shape with gases, they just take up whatever shape the container is in where you can find them. They also don't have a defined volume. You could change the volume at will. You can compress it, you can expand it. And so unlike liquids and solids, the gases are compressible. You can definitely change the volume. And ultimately, you can use the compressibility of a gas to um, help you out with processes such as refrigeration. But the solid, the liquid, and the gas phase, those are the states that we're going to be concerned with in this class. Not to say that they're the only ones. If you dwell deeper into the world of physics, you'll find out that there is plasma, there is condensed matter such as the Bose-Einstein condensate, but those are things that we don't typically look at in intro chemistry classes. But what we do look into though is a diagram known as the phase transition diagram. With this diagram, we can basically tell whether we have a solid, a liquid, or a gas. Simply put, this is a 2D diagram of pressure versus temperature. And as you can see, there are some boundaries that separate the solids, the liquids, and the gases from each other. The boundary between the solid and the gas is what we call the sublimation point. And in particular, turning a solid into a gas, which can happen for some substances, at least at room temperature, is what we call sublimation, shown right here. The process of turning a solid into liquid is what we do refer to as melting. And the process of turning a liquid into a gas is what we call evaporation. The processes are also reversible, so you can go the other way. You can turn a gas back to a solid in a process known as deposition. You can turn a liquid back to a solid in a process known as condensation. Excuse me, freezing. What am I talking about? And you can also turn gases into liquids. Now, this is condensation. All right, so what you need to know for the purposes of this class is the names, the categorizations of these processes. Whether you're undergoing melting. If I refer to condensation, you should know that a gas is being turned into a liquid. If I tell you that you're undergoing sublimation, you should know that a solid is turning into gas, etc., etc. All right, so these are physical changes. The exchange between the solid turning into gas or the gas turning into liquid or any of those iterations, you're still dealing with the same chemical. That hasn't changed whatsoever. And so you just change the physical form of the substance, and as a result, you refer to these changes as physical changes. It is when you alter the chemical composition of a substance that you now have chemical changes, and we'll be talking about those in due time. But now looking at a much more specific picture, we have here a phase transition diagram with actual pressure values in atmospheres given and temperature values in Kelvin. So a question like the one here can be asked. You have a pressure of 2 atmospheres and a temperature given. Looking at the graph for a pressure of 2 atmospheres, you're going to be somewhere up here. If you fall below the, about below 320, 310, you'll be guaranteed to be a solid. If the pressure is 2 atmospheres but you raise the temperature to 350, what happens is that at about 2, which is right here, at 350 you're all the way there. So you're no longer within the solid realm. Now you're in the gas realm, meaning that you have to be a gas. So raising the temperature up to 350 will definitely make you turn from a solid to a gas, at least that for the point of view of this molecule. If the pressure were to be raised to 3.4 atmospheres at a temperature of 305 Kelvin. All right, so 305 Kelvin will be roughly, roughly right here. And 3.4 atmospheres looks like you're going to be up in the solid regime. So you'll be dealing with a solid. And now if you keep the pressure at 3.4 atmospheres, but you raise the temperature up to 320, well, 320 is right here. And at 3.4 atmospheres, you are just slightly past the melting point barrier. So technically, you are a liquid at that point. Okay, so at 2.2 atmospheres, looking at this graph, and at 320 Kelvin, you are right on this point. And this point is what we call the triple point. And it's called in such a way because right at this point where all three lines, the boiling point, the melting point, and the sublimation point of the substance meet, basically you have an equilibrium among all three of the states. You have a solid, a liquid, and a gas right at the triple point. Okay, so you could further analyze this graph, and ask questions like the following here, and say if the pressure is 1 atmosphere, when do you have a solid? And at 1 atmosphere, you will have a solid so long as you are at a temperature below 290 Kelvin, because if you look carefully at 290 Kelvin, you tend to intersect with the 1 atmosphere. So below 290 Kelvin, you will end up being a solid. Above 290, at that particular pressure, you'll be a gas specifically. So this is how you look at the graphs. But oh, and I'll do one more question just to make a thorough analysis with the phase transition diagram. If you have a pressure of 5.8 atmospheres at 380 Kelvin, okay, 380 Kelvin is right here. 5.8 atmospheres, okay, this is 3.4. The difference between 3.4 and 2.2 is roughly 1.2. So add another 1.2 to this value, you'll get 4.6, add another 1.2, and you'll get, okay, so 4.6, you're 5.8, so you're going to be somewhere up here. And if you're going all the way up to your 380, it looks like you're going to be in the liquid phase. All right, now let's ask another set of questions that to some degree may be a little bit more important. So by giving you a specific temperature and a specific pressure, you can see whether you're dealing with a solid, a liquid, or a gas. But also, you could be giving a change in temperature. You could keep the pressure at 3.4 atmospheres, but you could change the temperature from T1 to T2. And in that particular case, you'll be looking at melting. Simply because at 3.4 atmospheres here, you'll be going from the solid phase into the liquid phase, right? And that process itself is referred to as melting, right? Because you're turning a solid into a liquid. In a similar fashion, if the pressure were to be constant at 1 atmosphere, okay, so we're now here, if the temperature is changed from 320 Kelvin, which basically means that you are here originally as a gas, and you change the temperature to 270 Kelvin, then you will be going past 290, which is the the cutoff between being a solid and a gas, into 270, which is now in the realm of the solid. So you basically would change a gas into a solid, and we call that deposition. You could also look at the opposite process. You could keep the temperature constant, 315, which is roughly somewhere here, 350 Kelvin. And in this example, we are decreasing the pressure from 6 atmospheres, which is probably going to be very high up here. And we're going to take it down to 1 atmosphere, in which case we go from being really high up here, past that line, all the way down here. Now, the thing about this specific example is that because you start really high in pressure, you actually end up starting at the liquid phase. And as you decrease the pressure, you have to go past the melting point, turning into solid. But then you go low enough that eventually you go into a gas. So you actually have to say all that. The liquid turns into solid and the solid turns into gas. Not the same thing as saying that the liquid turned into gas, right? You actually had to undergo freezing. You had to undergo freezing before you underwent sublimation. Those are two different processes that happen sequentially, as opposed to the liquid turning into gas directly, which is evaporation. So I just want to make that clear. Okay, so now here we have a substance that has a melting point of 5 degrees Celsius and 92 degrees Celsius. That's the reference 2 points of temperature. And the idea is that below the melting point, you're going to have a solid. In between the melting point and the boiling point, you're going to have a liquid. And above the boiling point, you're going to have a gas. So when I tell you the temperature is increased from -20 to 35 degrees Celsius, -20 is below the melting point, so you start as a solid. And if the temperature is raised to 35, well, 35 lies in between the melting point and the boiling point, so you end up in the liquid phase. And so what this tells you is that you go from solid to liquid. In other words, you have melted. All right, and we'll do one more example. We're going to change the temperature from T1 to T2, 120 to 100. At a temperature of 120, you are well above the boiling point, so you're a gas. And so decreasing the temperature to 100, well, 100 is also above the boiling point, so you're still a gas. So you actually haven't undergone any physical change. It's still a gas, but you're a little cooler than you used to be. That's all that's happened. Alright, so in the next video, we're going to start talking about substance classifications, and we'll start looking at mass conversions.